Hello everyone and welcome back. For our next video in Chapter 7, we're going to be talking about analyzing linear and exponential models. Now when we say analyzing, that basically means asking follow-up questions. So after we've written the equations, we're going to go ahead and ask some follow-up questions. What kinds of things can we do with these equations? And what would these things look like if we graphed them so that we can connect a visualization with the actual algebraic expressions that we're writing? So let's go ahead and read this first example. A science experiment involves periodically measuring the number of mold cells present on a piece of bread. At the start of the experiment, there are 50 mold cells. Each time a periodic observation is made, the number of mold cells triples. For example, at observation number 1, there are 150 mold cells. Part A asks me to determine which type of model, linear or exponential, would be best to model this situation and then write the model. Well, in order to determine that answer, what I need to do is look at the pattern. So I'm going to look at the pattern of growth or of decay. In this problem, if I go back and reread, it tells me that the number of mold cells triples. So the pattern would be that we are multiplying by 3 every time. As soon as you see that this is a multiplication pattern, you can say that you would be using an exponential model because we have a multiplying pattern. Now, if we wanted to write the model, the general form for an exponential model is y equals a times b to the x power. A is always the initial value. Now, the initial value here tells me that when we start, there are 50 mold cells. So I need to go back and reread the question to figure that out. The B is the pattern. How much are you multiplying by? Which in this case would be 3. So the equation that I'm going to come up with is going to be y equals 50 times 3 to the x power. And that would be the second part of my answer. Now the table here asks me to fill in the missing outputs. So I know that the pattern is that I'm multiplying by 3. Between 50 and 150, I would multiply by 3. Now I'm going to continue to multiply by 3 to fill in the table. So if I do 150 times 3, I end up with 450. If I do 450 times 3, I end up with 1350. If I do 1350 times 3, I end up with 4050. And if I multiply by 3 one more time, I end up with 12,150. Another way to approach this, rather than using the pattern, would be to use the equation. So in addition to seeing a connection between the table and the pattern, I also want you to see a connection between the table and the equation. This provides you with a really good way to make sure you've checked that your equation is correct. For example, if I type in 50 times 3 to the second power, because this would be my x, I would have 50 times 3 squared, which is 450, which confirms that this is the correct number for my table. If I do the same thing and I do 50 times 3 to the third power, I get 1350, which confirms that this is the right value for my table. If I do 50 times 3 to the fourth power, 3 to the fourth power, I get 4d50, which confirms this was the right number for my table. And lastly, if I do 50 times 3 to the fifth power, I get 12,150, which confirms that that was the right value for my table. So what I want you to see is the connection between the equation we wrote and the table, as well as the connection between the pattern we found and the table. We can fill in this table either way. It also provides us with a great way to check our answer. Now, Problem C is a follow-up question. What will the mold cell count be on the 50th observation? Now, if we look back at the way that our data is labeled, the number of observation is the X value. So if it says we want to know what's happening on the 50th observation, this would be an X value in my table. Now I could theoretically make a table like this that keeps going and counts all the way to 50 in the X row. However, that would be very time consuming and inefficient. A much more efficient way to handle this would be to take this equation that we wrote and simply plug in the number 50 for the X value in the exponent. Which, if I type that in on my calculator, is this huge number with this e and this 25 at the end. The e to the 25 really means times 10 to the 25th power. It's exponential notation. So we would have 3.59 times 10 to the 25th power, which is a lot. It's a really big number. And we're counting the number of mold cells. So you would write mold cells here as a label for your data. In these questions, it's going to be really important that you should always label your answers with either units or like data descriptions. So we're counting mold cells here. For part D, it says, what would you expect a graph of this situation to look like? Make sure to label any significant values on the graph, as well as the X and the Y axis. Now, when I say what would I expect a graph to look like, I'm not asking you to give me a super detailed picture. I'm really just asking you for a few things. When I draw this, I'm going to be asking you for, number one, a general shape. Number two, labels on the x-axis and on the y-axis. And number three, the initial value should be labeled. So if I were to graph this, because this is an exponential function and my numbers are getting larger, I would expect it to be an exponential growth picture, which would look like this. Now my labels would be, so this is the general shape. I'm doing this one in blue. The labels, when I say label your x and your y-axis, I'll do this in red. Here's what I mean. Under the x-axis, you should write that x, and I'm getting this from the table, is the observation number. And the y-axis, and again I'm getting this from the table, is the mold cell count. Last thing is the initial value. Now when I say initial value, I mean what are the important numbers here? Well, it's important for us to know that when this graph started, when x was 0, there were 50 mold cells. It was given to us in the original directions. It was also shown in the table. It's also part of the equation when we look at the initial value is 50. So that 50 should be labeled on the graph. All right, let's go ahead and go through another example. So another example of this process would be Julie gets a prepaid cell phone. Initially, she has a $40 credit on the phone. That means she put $40 worth of charges built into her account. Each minute of talking costs 15 cents. So every time she talks, a little bit of money gets taken off of her account because she basically spends this money she has saved up. Let x stand for the amount of time in minutes that Julie has talked, and let f of x stand for the remaining dollar value of the phone. Determine what type of model, linear or exponential, would be best to model this situation. So when I say determine which type of model, we know we need to look at the pattern. Now the pattern in this question is that the talking for that many minutes costs 15 cents. In other words, it's a subtraction problem. We're taking away 15 cents from my saved amount. Because the pattern is that we are subtracting 15 cents, this would be a linear model. So we would say that we chose a linear model because there is a subtraction pattern. Now, the general equation for a linear model is y equals mx plus b. The m is the pattern. How much are you subtracting or adding? So 0.15. The b is how much you began with, your initial value. Now, it tells me in the problem we started with $40 in our account. If I combine all this information and I make an equation, I would have y equals 0.15x plus 40. This should be negative 0.15x plus 40. All right, now let's fill in the missing outputs of the table. So we know that the pattern is that we are subtracting 0.15 every time. So to go from here to here, I just take away 15 cents. To go from here to here, again, I could just take away 15 cents, which is 39.70 cents. Then I could take away 15 cents and I would have 39.55. And then I could take away 15 cents and I would have 39.40. And then I would take away 15 cents and I would have 39.25. Now, another option here to confirm or check our answers would be to use our equation to confirm or check our answers. So if I use this equation and I plug in the number 2 for the x, I would have negative 0.15 times 2 plus 40. When I do that, I can confirm I get 39.70. Then I could do the same thing with the number 3. So negative 0.15 times 3 plus 40. Then I could do the same thing with the number 4. So I would have negative 0.15 times 4 plus 40. And I would confirm my answer. Then I could do the same thing with the number 5. And I would have negative 0.15 times 5 plus 40, and I would confirm my answer. Now you'll notice we were able to do the exact same thing with this equation that we did on the previous example, where we were able to find a relationship between the pattern and the table, as well as between the equation and the table. Now let's take a look at the follow-up questions. So the first follow-up question is find the value of f of 10 and explain its meaning in terms of the cell phone. So f of 10. Well, where is f? What is this? In the original problem, you will notice that it said let f of x stand for the remaining dollar amount. Now in this problem, the remaining dollar amount is also y. So f of 10 also means the same thing as find the y. Now we want to find the y value when the x is 10. And we need to sort of make a note to remember our function notation. So on the side, you might want to write f of x equals y. The x values are always inside of the parentheses in function notation, and the y values are always outside of the equal sign in function notation. So that 10 must be an x value. What that means is that f of 10 equals, now we take our equation, negative 0.15 times that x value, which is 10, plus 40. If we type that in on our calculator, we would have negative 0.15 times 10 plus 40, which is 38.5. Now we just calculated the remaining dollar value, so the label here on this answer would be the dollar sign. Next it says find the value of x that makes f of x equal to 10. So in this case, they're giving me the y value. So I would write 10 equals this equation that I came up with, negative 0.15x plus 40, and I would solve this. So I would subtract 40 on both sides, and I would have negative 30 equals negative 0.15x. I would divide by negative 0.15, and I would get that x equals 200. Now, what does this mean if I have to explain its meaning in terms of the cell phone? Well, if I just figured out an x, which was 200, not 22. If I just figure out an x, I know from the table that x is the number of minutes I spent talking. So when x equals 200 minutes, there are y, which is $10 remaining on the phone. And I know that because this is a y value. So to explain my thinking here, what I would say is when Julie has talked for 200 minutes, there are $10 remaining on the phone. Finally, let's sketch a picture of what we would expect a graph to look like. Again, I'm going to look for general shape. I'm going to look for labels on the x and y axis. And I'm going to look for the initial value labeled. So, general shape, let's start with that. Since this is a linear function, it's going to be a line. And since the pattern is that we are subtracting the same amount every time, it's going to be a line whose slope is negative. Next, we're going to label. Now, just like before, we're going to look at the table to help us with this. So, x-axis is going to be the number of minutes of talking. And the y-axis is going to be the remaining dollar value. Finally, I'm going to label the y-intercept, the initial value. The initial amount that I have here is 40, so I would label that on my graph. All right, that's going to be it for today. We will go ahead and finish this up the next time I see you. Thank you so much for watching, and have a great night.